Yeah, I hope everybody can see my screen now.
Yes, we can hear and see it.
Okay. So hello, everybody. My name is Sergi Siso, and today I will talk about how we expanded the target languages that we can target from Cyclone. I guess not everybody is familiar with Cyclone, and now in a second I will introduce the software. But first, let me say this is just not my work. There's a lot of contributors in Cyclone, and the main contributors are listed here. They are Rupert, Andy, and myself from STFC Hartree Centre, then Ivan Chris from the UK Met Office, and Georg from the Australian Bureau of Meteorology. So the problem that we are trying to solve is one about managing complexity, and that's because the big HPC software simulations, like the ones we see in climate and weather models, are getting more complex in different aspects of the software. One is in the software itself. It's becoming large. There's a lot of science involved, and some of the science code was written years ago, so we also have legacy code, and they might have a lot of contributors coming from diverse domains of science, maybe not all of them knowing the best practices in HPC, all contributing in the same software. So this is a first challenge. It is often called maintainability or a productivity challenge. But then on the other hand, we also have a challenge to make it performant in modern systems. Modern systems, we have parallelism in different levels, and we want to make use of all this parallelism. We may also have accelerators providing most of the computing power of the systems. So it's important to make use of the accelerators. And of course, memory subsystems with caches, which are fundamental to get good performance. And maybe even we want to make the software run well in different systems, and we want performance portability, which makes the complexity even harder. And the problem with all these different software requirements that we have is that they compete with each other. So sometimes, let's say if one wants to be performance portable, one might decide to write the software twice, but then that's a big penalty on the portability, on the productivity of the application. So we have to find a balance between these three software requirements. This is sometimes referred as the 3Ps problem. And there are several solutions, but one elegant solution, I would say, is the compiler abstraction. This is letting the software being written independently of the parallelization and optimization strategies, just the scientific code as an input to the compiler, and let the compiler or the code generation system take care of the optimization and parallelization of this system. And Cyclone is one of these solutions. Cyclone is a configurable finite difference, finite element compiler, where the scientist writes the input code as a higher level description of the algorithm and a lower level description of the kernels. But what they write is decoupled from the parallelization and optimization specific from the system. But maybe different from other compiler solutions, we also have an entry point for HPC expert to fine-tune or inform how the optimizations are going to happen in the system. So the compiler is not completely automated. We have some parts automated, but still we let the HPC experts in what we call recipes, which are essentially Python written transformations, inform those decisions. So basically, this is how the structure of Cyclone looks. Again, the scientific domain-specific software is written in Fortran. It's basically an embedded DSL with some metadata. And then we have an application frontend that parses this software. It is aware of some of the concepts, and some other concepts are passed as metadata in this code. And then it transforms this into our internal representation. Here in this internal representation is where we have the second entry point for the HPC experts, where they can write these recipes to explain how to parallelize or optimize this code. And when these transformations are done, we send that to a Fortran backend and generate the output, hopefully parallel and efficient Fortran code. So here is an example of these scripts that we let the HPC experts write to do the parallelization and optimization. I'll go through this one. This one specifically is taken from the Alfric model from the UK Met Office. And this is a very simple example just to show how Cyclone works, that it's coloring and parallelizing the application. And this is basically done with two loops, one that traverses all the statements in the code and looks for loops that are iterating over cells and are not in discontinuous spaces. And it applies the coloring transformation to all these loops. And then we have a second loop after that, that again traverses all the loops in the code. If they are a colored loop, it adds an OpenMP pragma to the inner, to the second outermost loop, or an OpenMP pragma to the outer loop for the ones that are not colored. So that's all what the description is. And with that, we can parallelize with OpenMP a whole code base, because we apply the same script through all the different source files in the code. So we can use Cyclone with a few different applications. As I said, maybe the main user of Cyclone is the Alfric model, which is developed by the UK Met Office. It's currently in development, and it should be the successor of the unified model and become operational in a few years. But that's not the only application that uses Cyclone. We also have a front-end, experimental front-end from the NemoLite model from the European Weather and Climate. And also the Australian Bureau of Meteorology is evaluating Cyclone for their ROMS ocean model and the MOST tsunami model. These are all production codes. So we have some maybe smaller or simpler codes in an internal Cyclone benchmark suite that we have. And specifically, one of the applications in this benchmark suite is NemoLite 2D, which is mostly the results that I'm going to show today. And this is interesting for us because we have manual implementations of all these with different backends for this application. And this is very helpful because we can compare the Cyclone generated code with the manual implementations. So this is the first plot that I want to show for the general or basic usage of Cyclone in a single node. Here with this light blue, we have the manual implementation of NemoLite 2D application for serial OpenMP and MPI. And you can see that if we apply Cyclone without any transformation, at the beginning, we lose a little bit of, well, we lose quite a few performance just because the way in which the scientific code is written, where the high-level algorithm is in one part and the kernels are on another, is not very prone to inline things perfectly. But if we then, inside Cyclone, apply the inline transformation, we basically recover all the performance and we get at least as good performance as the manual implementations that we have. And then another basic thing I want to show is that, of course, because we can generate MPI from Cyclone, we can target multi-node scalability. Here is an example of weak scalability. And weak scalability, I increase the problem size proportionally to the number of cores. So the ideal scalability is represented by an horizontal line here. And you can see in this simple application, which maybe it's not even sensible to scale it to these numbers, but it already scales to more than 1,000 cores. This is the only slide I'm showing in my presentation for multi-node scalability. If you're interested in multi-node scalability, I would recommend looking at the different Alfric presentations or information that we have around. But today, what I want to focus more is there is still one question to solve from PScyclone, which is how do we deal with the different heterogeneous hardware landscape that we have. So looking at the top 500 list of machines, we can see that there is very different processors from different vendors, and also a lot of the machines have accelerators, which can be also very different. And we believe this is only coming more and more diverse with the new additions from Intel and AMD to this list. And even worse if we consider novel alternatives like FPGAs and this kind of novel devices. And the question is Fortran with directive alone going to be enough with this diverse ecosystem? And probably we are missing some of the APIs that the vendors favor for these accelerators and hardware. And it would be great if we could get PScyclone to generate them. So to realize this, already a couple of years ago, we started with this vision that trying to have in the center of PScyclone a language-independent internal representation. Well, we call it the PSyIR. And the idea is to have the different front ends produce this common language independent representation. Then all the transformations apply on top of this PSyIR. And then we can produce different backends that target different languages. So we started developing this with 2 European projects. One is called EuroExa, where we ported the NemoLite 2D, which is part of the GeoOcean frontend, to an OpenCL backend, with the idea to ultimately target FPGAs with OpenCL. And also as part of Easy Ways, we developed a SIR backend for Nemo. SIR is also another internal representation, which is developed by the MetaSwiss, and it has their own set of tools that we can interact with thanks to this backend. So looking at this, my reasonably be skeptic about translating whole language to language, because, well, there isn't many transpilers around that can fully convert Fortran to C, because truly it's a very hard thing to do. But this becomes more feasible if we are not targeting to convert the whole language feature set, but if we limit ourselves to a specific set of features from the languages. And this is already enough for us, because what we are interested into accelerating is usually the computational kernels. And these are often limited to a subset of the language, which is usually control flow, arithmetic operations, data accesses. And these often have relatively direct translation from one language to another. Also, we have this concept on our AST3 of a PSyIR code block, which is basically representing a snippet of code, which is specific from one language. Can be Fortran, for instance, but our parser or our internal representation is not able to understand exactly what it does. This is good for us because we can provide a file-safe conversion from one language to another, where maybe we cannot translate 100% of our kernels, but we can translate 80% of them or 90%, and we can see it still works. We can test this part of the application, and we can see which features we need to develop next in order to have a 100% coverage for the specific application. And this so far has worked quite well. So this slide is a bit dense with code, but I wanted you to just give a look onto how our internal representation looks. Here in the top left image, we have an example of what the scientific code looks like in the higher level. This is what scientists would write. And if you look just at the first kernel that they call it, is discontinuity kernel, PScyclone then translates this in something similar to what we have here in the bottom left corner. You will see we have not applied any transformation here yet. So it's basically iterating over the individual elements of the loop in a quite linear manner without OpenMP or anything, because we have not applied any transformation yet. And when we call this specific kernel, the continuity kernel, it is also able to represent all the internals of the kernel in this language agnostic internal representation that you have in the right-hand side. So with that in mind, how can we do to translate or to output OpenCL code from NemoLite? So here the basic requirement that we had is we do not want to modify at all the scientific code. This is still the algorithm code and the kernel code, which is in regular Fortran, completely unmodified, and even maybe calling other Fortran libraries. So PScyclone parses all this scientific code, and it generates these 3 layers: an algorithm layer, a parallel system layer, and a kernel layer. So to generate OpenCL, we can maintain the first 2 layers, the algorithm and the parallel system, still in Fortran. We do call OpenCL, but we call it using some Fortran bindings for OpenCL, which are in a open source project that we have at GitHub called Fortcl. And really the only part of the application that we must convert to OpenCL is the kernel bits of the code. So that's the only part we need to translate. And to do that, we can do it with this minimal script that I have here. It basically has 2 mandatory steps. One is that inside the OpenCL kernels, we don't allow global variables. So we have a way to get rid of these global variables. And then we just say to the part of the code that has to be scheduled into OpenCL devices that we want to apply this OpenCL transformation into it. Then optionally, there's a 3rd step, which is maybe fine-tuning a little bit more the OpenCL options in order to get better performance out of it. And just with this minimal script, we can get this performance in the plot on the right-hand side of this slide. Basically here it's compared against a manual implementation in OpenACC of the same code. And it's just with this minimal script a little bit less performant. But I also made a roofline analysis of this application. We know this application is bandwidth limited, and we are still not optimal. Maybe we can do some more optimizations if we make the script more complex, but we are approaching near optimal performance. I think for this OpenCL in the NVIDIA V100, I was getting 370 gigabytes per second out of the 600 and something that this application can provide. So I think that's already quite a good milestone. And the OpenCL generation, it's available on our latest release of PScyclone. But that's not all. I think that's just the beginning. This being able to produce output code in different languages opens the door to a lot of possibilities. And we are currently working in 2 other projects. One is still EuroExa, which our output code for FPGAs is still not perfect, basically because the OpenCL that targets FPGAs, it's substantially different than other platforms, and we are experimenting using OpenCL tags and Salnik's specific pragmas together with the OpenCL. And also this last year, we started a collaboration between the Hartree Centre and some ECP partners to look at the new C++ frameworks that have very nice solutions for performance portability. And we started thinking about if it is possible to develop a backend for Cyclone that generates Cocos code. And to create these C++ frameworks, the overall architecture is similar to what we did in OpenCL, but maybe with a fundamental difference, which is that we want to generate part of this intermediate parallel system layer that we have in Cyclone as the target language, is C++ Cocos in this case. However, also another part of this layer has to be kept as Fortran, because we have to interact with the Fortran libraries or the part of the algorithm code that we cannot translate to the target language. So we came up with this architecture with a two-level parallel system layer, where first we prepare all the functionality that we need, as or row pointers or function wrappers to the libraries, and then we call the target language. And we are not able yet to generate this code, but we have already created manual versions of the NemoLite application using this target language and done performance portability analysis through different architectures. And here are the results. So you can see that there's quite a few interesting results already. I think one of them is that surprisingly, maybe C++ with OpenMP already gets better performance than the Fortran. And I'm saying surprisingly because this is semantically basically the same code. It just changes the syntax from Fortran to C, but it turns out the compiler was able to optimize it here a little bit better. Then we created two different implementations of Cocos. One is using their own data containers called views, and the other is just working on top of the raw Fortran data structures. And the one with views, it has a little bit of overhead compared to our C++ or Fortran OpenMP. However, this one allows us to manage the synchronization and go to the GPU's architectures very easily. And then we have the other implementation with row pointers that in the cases of the CPU is the one getting the best performance. So already I would say it's not perfect if comparing to the optimal performance as given by the roofline analysis. We still have some way to go, but we can already see a correlation of the performance to the optimal performance for most platforms. As you can see, we have an outlier here with the AMD GPUs, but to be honest, we just tested our current implementations with AMD GPUs. We have not time to develop in this platform, so hopefully when we look this closer with the profiler, we can optimize this implementation as well. And finally, from this chart, I also want to note something which is probably just a curiosity right now, but we can see that in each of the platforms, the best performing backend is a different one. So in the Intel CPU, it's the Cocos with row pointers. In the AMD CPU is the C++ with OpenMP. In the NVIDIA is the OpenAC code, and in the AMD GPU is the OpenCL code. So as I said, because this is still in development, it might not be true in the future, but this already shows this picture that performance portability can be very difficult, and it's good to have options because different vendors sometimes maintain or develop their solutions thinking in different programming models. So it's good to have all these options. So I'll finish my presentation with a takeaways. So if you remember something after these presentations, probably these are the main headlines. So PScyclone is a domain-specific compiler, and we focus specifically or especially in the separation of concerns between the scientific code and the optimization and parallelization code. And we also focus quite heavily in the performance portability and thinking how we can make it easy and productive and portable to write code. But the HPC software and hardware ecosystem is getting wider in our opinion. There's lots of options, and it's good to interact or being able to create solutions with all these options. So to tackle this challenge, we created the PScyclone CIR, which is a language-independent intermediate representation, and we have a few ongoing projects trying to support new backends and improve this language interoperability or language-to-language transformation. This is my last slide. PScyclone is open source, is available in GitHub. We also have read the docs with all the documentation. And if you want to install it and try it as a user, it is available in the Python package manager and also in Spec, which is available in few HPC systems. So thanks for listening, and I'll be happy to take questions now. Okay, so see the first question, if I'm aware of the different DSLs projects in Europe and creating common AR. Well, I don't know if I'm aware of all of them, but I'm aware of quite a few of them, especially in the climate and weather domain. In fact, we have this common project that I talk about called EasyWeight, where we collaborate with different partners from different countries in Europe, and we try to create or have the possibility to interact from one AR to another AR. So yes, that's something we look actively. The second question I see is if it's NemoLite available for download. Yes, it's in GitHub. It's in our PScyclone bench. That's the name of the project in GitHub, and there is 2 applications inside this GitHub repository, so it's open source and available there. And the last question is the ultimate goal to apply the tools you have used, NemoLite and Nemo itself. Yes, but the Nemo frontend, it's a bit different in that it doesn't have metadata. We are trying to parse the Nemo code as it is and trying to get the higher level concepts from it. So the ultimate goal, yes, it is to apply all these backends to Nemo if we can, but that's probably still far away. I think now the main output that we generate from Nemo is Fortran with OpenCL. In a project we collaborate with NVIDIA to generate accelerated code from Nemo. But yeah, the ultimate vision is to have this all-to-all front ends to backends and being able to use the backends with all our applications.